Carbon is an atom that has hybridized orbitals, which means that unlike other things, carbon has all of its bonds in a tetrahedral arrangement about the central carbon. In this case, this is a C5 molecule, okay? Now, carbons all have to have 4 bonds, and so this one would have to have 3 hydrogens, 3 hydrogens, 3 hydrogens, and 3 hydrogens. So this would be C5H12. This has 5 carbons. This one would have to have 3 hydrogens to complete its valence. This would have to have 2. This would have to have 1, 3, and 3, which means this is also C5H12. This one is C5. 3 hydrogens, 2, 2, 2, and 3. Again, this is C5H12. So what this means is that all 3 of these molecules are exactly the same in terms of their chemical formula, but they're different in terms of their skeletal structure, which means they're going to have very, very different capabilities and different properties in our bodies and in nature, because in biology the most important thing is shape. So speaking of that, this is a completely saturated molecule. There's complete movement around these bonds. These guys can spin, okay? But notice how this guy can close pack to this other guy. This is how butter works. Butter is a saturated fatty acid. So butter have much longer carbon tails, but they can close pack. That's why butter is solid at room temperature, as opposed to this guy, okay? So this, there's no movement about a double bond, none. And so this would be what olive oil would look like. So there's one area with no movement, which means that when I put another olive oil close, it's not going to be able to close pack. These are going to slide past one another much more easily than these guys that are completely bound to one another by that close packing, okay? Now, another thing, carbon can triple bond to itself, to another carbon. So this is a C2H2, okay? Now, looking at our counts, this is our C5H12, but I put in all the hydrogens this time, okay? This guy has the 1 point of unsaturation, okay? So this would be the one that's like olive oil. So this has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have C5H10. This one was C5H12 because it was completely saturated. With a double bond, it's C5H10. This has 2 double bonds. So this is going to have 1, 2, 3, 4, 5, 6, 7, 8. So this one has 2 points of unsaturation and is C5H8. So we went C5H12, C5H10, C5H8. This one has a triple bond. Triple bonds act like two separate double bonds in terms of the unsaturating things. So this one also is C5H8 because it's as if it has 2 double bonds. So one triple bond acts like that in terms of saturation, but not in terms of shape and not in terms of function. So this one will be different than this one in a biological reaction, okay? The last things I want to talk to you about are cis and trans. So you've heard of trans fats. So these guys are Eldorado colors, but they really represent big, long carbon molecules, okay? In this case, so hydrogens are the least important type of thing, okay? So hydrogens would be together, and the important stuff would be together. This is a cis molecule, so these are together on the same side, that's what cis means, with a double bond. Because there's no motion, this doesn't spin, this is permanently like this. This doesn't spin, this is permanently like this as well. So these are permanently on opposite sides of this plane, okay? As opposed to this guy, these can spin, it looks like they're in different places, but I can just spin it around and suddenly they're in the same place. So this is what we mean by no motion around a double bond, okay? Now, this guy over here, I want to talk about two things about this. Number one, these are enantiomers. So these are mirror images of one another. What that means is these cannot just overlay on one another. If I match up my orange and my green, then suddenly my yellow and my white are not matched up. But if I go, okay, well, I'm going to match up my yellow and my white, then suddenly my orange and my green are not matched up. But when I look at them like so, oops, if I can do that, there we go. They're mirror images like your hands. This one could be active in other words, if you're owning a pharmaceutical company someday, and both of these will come in different ratios. It's not going to be 50-50. If you're making these as a medication, then some of them will end up like this and some will end up like this. First of all, that's an issue in terms of wasting your reactant. These are really hard to separate because they have basically really almost exactly the same properties. So you need to figure out how to get rid of this guy if it's wasting your reactants. Okay, so if only 30% are the type that are going to be active in people or animals, then why waste 70% of your reactants making this and your time? So the thing is, you as a pharmaceutical need to be aware of money, but more than that, there's a possibility that this is active and does everything it needs to do, and this is toxic. So enantiomers are a really big deal in terms of pharmaceuticals. The last thing is when we talk about DNA, everybody always talks about, oh, it's a 5' to 3' molecule. So one side is 5', one side's 3'. What the heck are they talking about 5' and 3' carbons? Well, I want to tell you how people count carbons. Whatever is the least important molecule that a carbon is attached to is going to be the hydrogen. Okay, so basically what happens is then we number these in order based on what their properties are. So these are just colors, but they would normally be other things attached to these carbons, some of which would be more important and some would be less important. If the most important so we put the hydrogen to the back, okay? If the most important carbon, the most important thing this central carbon is bound to is the orange, and the second most important is the yellow, then this guy is going to turn basically in one way. It would turn like this, going important, less important, least important, or least important besides the hydrogen. Whereas this guy would turn this way. So if they turn left, that's called levorotary. If they turn right, that's called dextrorotary. All amino acids that anything on Earth uses are L amino acids. That means they're levorotary amino acids. Now, when we talk about DNA, when we start talking about important things attached to carbons, this is what I'm going to talk about, is basically the least important thing, and then we have to number the other stuff that the carbons are bound to. Okay, so when we start talking about 5' carbon and 3' carbon, it's because of what else they're bound to. Okay?